Thank you, everybody, for coming to this seminar of the Institute of Astrophysics. Today, we have the great pleasure to have with us Foteini Lykou. Foteini actually did her undergraduate at the Department of Physics here at the University of Crete a few years ago. And then she decided that Crete was not sufficiently exciting and she had to move to another slightly larger island. So she moved to the UK, where she did her postgraduate studies, both her master's and her PhD, at the University of Manchester at Zoderbank, under the supervision of Albert Zylstra. She continued on with postdoctoral appointments, visiting positions. She passed through the Observatoire de la Côte d'Azur in France at the University of Sydney. And her first formal postdoc was in Vienna at the Institute of Astrophysics. And then she moved to the Far East at the University of Hong Kong, which is appropriate considering the fact that she had an English education. And then after that, recently she moved back to the old Europe and she has started her appointment at the Konkoly Observatory in beautiful city of Budapest, where she's studying disks, stellar disks with interferometric techniques. So today we have the great pleasure to hear her presentation on the power of interferometry, finding disks in evolved stars. Foteini.
Thank you, Vasilis. Thank you for inviting me for this talk. I wish I was there with you in better times, of course, maybe next time. So today, as you said, I'll be talking about disks in evolved stars. An example here is as you see the first image is the planetary nebula of the Bug. And with, you might be able to see that there's a thick and a dense torus in the middle of its waist. So let me bring a quick outline of today. I'll be talking mostly about the last stages of evolution in intermediate mass stars, so from 1 to about 8 solar masses, and especially that the time after the AGP until they become planetary nebulae. I'll give you a brief introduction of the interferometric techniques we have been using and how we were using them to find disks in these evolved stars. And then I'll just do a quick summary of the work I've done so far with my collaborators, of course, in planetary nebulae and AGB stars, and also give you some future perspectives of what we expect to have in the next year, hopefully. So now, why do we care? I spoke about planetary nebulae. I spoke briefly, mentioned AGP stars. Now, as you see in the photo on the right, planetary nebulae come in various shapes. There's about 3,000 or so in our galaxy and about 1,000 in the Large Magellan Clouds that we know of. And 80% of those are not exactly spherically symmetric. So they don't look like the large sphere you see in the top left of the image, but they have more intricate shapes. That could be bipolars, they could be irregulars, they could have jets or knots in them. And the question was, I mean, more than 40 years ago when the first images came out, especially with later on with Hubble, why do they have this kind of shapes? What makes this? One hint will be if you have a binary system. And that's more or less what the population synthesis has been suggesting so far, that you would have a lot of multiple stars anyway. So perhaps you could also find them in planetary nebulae. Let's see here. So this first hypothesis, when the first images came out, was back in the 80s and also in the 90s, where the theoretical perspective were in order to build in simulations a bipolar nebula, you will need a dense equatorial waist to force the ejecta in the 2 lobes. And of course, to make an equatorial waist or a disk, you will need a binary system. So there's been a lot of work in the last 30 years or so of trying to find those binaries. But there are some problems, of course, because you have to take into account how distant the objects are. You have to take into account what is the orbital separation and the relative brightness. So can you actually detect them? If you could be looking at spectroscopic monitoring or photometric monitoring, but that could take years depending on the orbital separation. Imaging is more difficult unless you have a very high, a large telescope or Hubble. There is also a hint of whether you have a synergy with magnetic fields. Now, I will be talking a lot about this magnetic fields now, about their influence. But I just wanted to mention that there's thought to be a synergy between binarity and magnetic fields in terms of shaping bipolar BN and their jets. Now, this kind of equatorial wastes, are they dense tori? We didn't really know if they're tori or flat disks or accretion disks or circumbinary. We didn't know what types of binaries could shape different types of objects. But what we do know is that since they're very dusty, because we see that in the infrared, they're quite bright, some of them. And then we needed to find how these are formed, because we know that basically most of the material comes from an AGB star. And since AGB stars are dust factories, basically all this material is from the envelope of a single star or one of the companions. And I'll be talking a bit later about how we can find some hints on to look for these kind of binaries, perhaps, not just the shape of the nebulae, but basically because these disks are very small, we're talking about scales of less than 0.1 arc seconds. What you will really need to look inside, it will be interferometry, because you will need a very high angular resolution. And at best, a single dish telescope of about 10 meters can't give you such a good resolution, unless, of course, your object is very nearby, let's say 100 parsec or something. Now, just a short intro on interferometry. I'm not going to go into too much detail, just to show you what we've been using so far. So one of the main instruments we have using in our research is the VLTI, which is the Very Large Telescope Interferometer. And you see an image here of the platform in Paranal with the 3 AT telescopes. That's the small ones, 1.8 meter diameter, and the 4 large UTs, that's about 8 meters in diameter. And the VLTI, which is, you can see the lab compound in the middle of the platform. It combines light from at least 2 telescopes, or it used to. Now it's a bit more complicated, so you can do imaging interferometry. But let's focus now on the older instruments, which is the mid-infrared interferometric instrument. That one was a 2-beam recombiner, so it will combine light from 2 telescopes, and it's a 2-telescope interferometer. Either with the 2 ATs or the 2 UTs, and depending on the combination, you will get also a different baseline length. So from about 10 meters with the ATs to a maximum of 130 meters. And that actually was pretty good because it offered excellent resolution, theoretically speaking, about 6 milliarc seconds with the longest baseline. And the thing is that with the interferometer, you don't actually measure, you don't see an image, let's say. That's not what you record. What you record is visibilities. And without going into too much detail here, just to mention that if you see, what you record is close to 1, well, basically, let's say the visibility is a Fourier transform of the intensity distribution, roughly speaking. And when you see, it has usually a value between 0 and 1. If it is 0, it is your object is resolved. If it is near 1, the object is unresolved. So what I'm showing you here is that you will need a pretty good, on the left is the theoretical coverage you will get from the baselines with the UTs on the VLTI. With MIDI in particular, you only get 2 telescopes at a time. So to get an image like that, you will need more than 1 night of observation. So you have to go consecutively from one to the other. And you will build your Fourier transform of your, so the UV plane, the Fourier transform of the sky. And what you will get is visibility. So in the model you see on the right, you see that with the shortest baselines, which are the yellow points, and these here are spectrally dispersed. That's why you see them. It's not exactly points, it's long vertical lines. Your 10 milliarc second Gaussian will be barely resolved. But when you go to the longest baseline, so the green points, you're actually you're able to resolve your object. So based on that, and using this technique, now, as I said, you can't really do imaging. So everything you get with MIDI will be model dependent because you only have, your UV coverage is not perfect like it would have been perhaps with radio interferometers. So you have to base everything on modeling. Now, one of the first objects that we observed back in 2006 was the planetary nebula Menzel 3. Now, this is you see here, it's a bipolar planetary nebula. It has rather exciting features and different hourglass shapes. It's possible that it has also an X-ray jet. We'll presume that you will have some accretion. And of course, you will have a binary system. Its core is not resolved. As you see in the visual image, is very bright. The image in the middle, which in the red, that will be the nebula in the mid-infrared, so at 8 micron. And you see that the core is still unresolved with a single telescope. That's with one of the UT telescopes and Vizier instrument. And with MIDI, we were able to detect the first ever bona fide disk in a planetary nebula. So what I mean by that is, as I showed you earlier, what you get here is from the MIDI is visibility. So in the image I have here, the model is the dashed line, and the actual data is the bars that you see. And what you might be able to notice is within the figure, I'm mentioning the different kind of projected baselines you see, you get from MIDI. So when you are in a baseline, which is at around 1 degree or close to 0, so aligned on the minor axis of the disk, you see that the object is kind of unresolved. So it's a visibility of around 0.8. And as you go closer to the midplane of the disk, so around 80 degrees, you start to resolve a structure. So you see something that is small in one baseline and becomes bigger as you move along the midplane. And now for this, we used a dusty stratified disk with an MC3D model. And basically what we find here is that we're talking about a moderately flared disk. So it has a certain flaring is not exactly flat. The inner rim is about 9 AU from the central system. So that's quite close to the central engine. We were not able to see the star because it's hidden behind the dust anyway. So the disk is edge on, so you wouldn't be able to see anything inside it. And the mass of the disk is about 10 to the -5 solar masses. Now, let me continue on with planetary nebula M29, which was chosen as a spectroscopic twin of Menzel 3. That was one of the first reasons. And in what they were observed almost simultaneously. As you'll see here, it's also a very elongated bipolar nebula with a very bright core in the visual and also in the infrared. So it is not possible to see the central star or stars here because there is what they call a lighthouse effect. So with observations in the last 20 years or so, you can see something that looks like a beam moving around the nebula, and that from that you can infer a period of about 90 years for the binary, which is of course a white dwarf, and the companion might be a main sequence star. What's also interesting here is the ALMA, which has been, of course, a very good instrument for us in studying the evolved stars and the molecular emission. ALMA has found 2 rings. So we are talking about 2 separate ejections. Possibly the most recent one was about 900 years ago. Now it depends, of course, what kind of distance you assume for this system. But let's say, roughly speaking, about 900 years ago was the last ejection, so the inner ring that you see. And that matches quite well with the kind of nebulosities you see in the visual. And again, MIDI was able to find a disk. This is a very small source. As I see here, is about what was detected was about 50 milliarc seconds, but the true scale of the source, the true size of the source, can only be inferred by modeling. And again, here we used a similar model with, oh, I forgot to mention that the disk, both in Menzel 3 and also here, is just silicate-rich dust, so it's amorphous silicates only. And so assuming, of course, that these are oxygen, the parent star was an oxygen-rich star. And in this case, the fit was not exactly perfect because we didn't have enough data. I showed you earlier, we get 6 baselines for Menzel 3, but here you only get 4. So your coverage of the structure is not ideal. Still, again, we find here that the disk is not exactly flared. It's close to, the flaring is close to 1. It's a bit further out from the inner rim is further out from the central system, and it's a little bit more massive. But the model we used could not fully explain an excess in the mid-infrared, so about 25 to 50 micron. So there might need some changes in the future. Now I'm talking about 2 planetary nebulae. Let me go briefly to a Sakurai's object, which is a born-again star. And I don't know if you're familiar with them. So it was discovered in 1996 by an amateur astronomer, and it was thought to be a nova, a new nova. But it turns out that what we think nowadays, it's a star that experienced one last thermal pulse. And so it's a very large thermal pulse of VLTP object. And it has reascended since the post-AGB star track. So it was going down the white dwarf path, but resurfaced as a post-AGB star. It's a carbon-rich star and hydrogen deficient. It has a round nebula, which was discovered only within a year from the discovery of the star. And it's a very old PN. It's a very large PN. It's about 30 arc seconds in diameter. And the strange thing with this star is that it started brightening in 1996, but within 3 years, it dropped to a visual magnitude of about 22. So you can't see the star anymore. And the reason for that would have been that it is producing so much dust that you can't see it anymore behind the dust. So a recent paper came out and tried to estimate the amount of dust that's been produced by this star in the last 20 years. So we're starting about, you see an order of 5 increase in the solar masses according to the models from 98 to 2016. Now, another important thing for this one is that it might be actually rebrightening since 2015. It's a tentative data, of course, But you also see that from 2008 to about 2020, its brightness is increasing in the K band and also in L and M bands. So that tells us something about the star and the dust around it. And we had some observations again with MIDI back in 2007. What we found is a very small object, very compact, so 30 by 40 milliarc seconds. That's pretty small. And again, we used a similar model interpretation for the disk. It wasn't exactly ideal. We could fit the SD easily within amorphous carbon disk. But as you see in the visibilities here, the model is not perfect. So it might be that the model we'll be using is not exactly ideal for this type of object. But what was also interesting for us was that the orientation of the minor axis of the disk, so in the image you see below from the model, you see basically it's an inclined disk. So you see the bright, sort of the dark region is basically one part of the back of the disk itself because it's inclined towards us. And its orientation is aligned very well with a gap, an apparent gap in the planetary nebula, which was ejected thousands of years before that. And so at the time this came out, it wasn't exactly believable, perhaps, by the community, but just a few years ago came another paper, and it shows that this star has actually ejected a new nebula, a new bipolar nebula within the old one. And it's the direction of the ejection is very similar to the direction of the minor axis that we find from the modeling. And this nebula is quite small, or was quite small back in 2013. We are waiting for new data by Hinkle and Joyce. And the companion, of course, if there is a companion, because as I mentioned before, if you have a disk and a bipolar nebula, you would expect that you have a binary system, but it's still elusive, so you can't really see, unless, of course, we will be able to, in the future, to look inside again if the star is rebrightening or not. And so I've been talking a lot about PN and their disks. Let me go a step back to the previous phase, the AGPs, because the idea was, if you can find disks in planetary nebulae, can you catch them at an earlier stage when they're actually being formed? So if you were looking at AGP stars, would you find something similar? So flat or flared disks. So the picture here is completely different because you see plenty of, and it's not a comprehensive list, there are more observations, and most of them I present here are from ALMA, actually. So it's molecular gas, and you see that there have complex shapes. There could be spirals, there could be some formations look like flowers. You also get bipolar jets, so it's quite complex and not unlike what you also see in the planetary nebula, except you don't see spirals there. So I'll go into this more a bit later. Now, how do you look into AGP stars? Of course, you can go through a long baseline interferometry like you had with MIDI, with a VLTI, but those instruments were not imaging instruments at the time we did this research. Now they are, we have new instruments on board for the VLTI. And what we wanted to do as a quick study was to actually get images with a single telescope before even applying to get time, because as you can understand, it costs a lot to use the VLTI for an entire night or even 2 weeks to make a proper image of a star and its surrounding area. So a quick study will be with a single telescope with interferometry, and in this case, there is a technique called aperture masking. What you basically do, you introduce a mask in the light path as it comes from the telescope. So you'll see below it's an image of the telescope pupil on the camera and what it looks like when you introduce a mask through the system. And in the case of this particular mask, you have 9 holes, so it's a 9-hole interferometer, and you get 36 baselines instead of just one that you did with MEDIN or with VLTI in the early days. And you get the Fourier transform. You get, of course, an interferogram in the camera, and you get the Fourier transform of that. And of course, you get a visibility in what you actually like to use in this case, because you have such a very good UV plane coverage, is closure phases. Because, and without going into too much, that's the part that is not actually the Fourier data that's not exactly affected a lot by atmospheric transmission. And you can use that basically to reconstruct the images, so to get the image back from the original data. So we used, this particular instrument we used is called SAM, so sparse aperture masking on NACO, which is the near infrared camera on the VLT. And you get baselines between 0.8 and 8 meters. So basically, with a VLTI, you've been exploring ranges between, say, 6 to 20 milliarc seconds. Here you go to intermediate spatial scales, so between 20 and perhaps 100 milliarc seconds. And beyond that, you just need a single telescope anyway, so you wouldn't need aperture masking, just do simple imaging. This technique has been proven to work quite well for young stars and certain AGB stars. And I'll just show you a few images here of spirals. And these were discovered with the Keck telescope. So it's a 10-meter telescope, another aperture masking experiment there. And we tried to employ this this technique for a few AGB stars. The first star I'm going to talk about is L2 Puppis. It's an oxygen-rich AGB star. And it has a period, so a pulsation period of about 150 days. But if you look at the long-term life curve of about 120 years, you see that apart from the individual pulsations, there is a long-term effect that is quite strange. And an earlier paper said that the plausible cause of the fading in L2 Puppis, and I'm talking about the fading after 1990, is the extinction by circumstellar dust. So if you have extinction by circumstellar dust, you should be looking, of course, in the infrared and to try and find it. And that's what we did with NACO. We look into the K and L band, so around 2 and 3.7 micron. And what I show you here is an image in the mid-infrared with a single telescope, so just simple imaging. And you see that the source is basically unresolved. It's kind of oblong, so it's not exactly spherical, or it doesn't appear spherical. But if you look closer with aperture masking, you are able to finally resolve the structure there. And this structure is like a torus or a disk, as we know now, with a radius of about 4 AU. So the size of the entire structure is about 8 AU. When we were able to determine that, well, first of all, the central star is unresolved, so you can't really see it anyway because the disk is also edge on, but it has to be less than 28 milliarc seconds. And we also were able to determine that the stellar mass was about tentatively 1 solar mass. And we're still not certain if there is a companion at all, because we weren't able to find a good signal from this data set. But that star doesn't only have a disk, it also ejected a nebula. So you have a bipolar nebula that was ejected probably in the last 15 years or so. And that can only be seen in scattered light. So it's the image I have here in the middle, a scattered light with a sphere. I believe this one is a combination of H alpha emission and also infrared emission. And not only does it have a disk and a bipolar nebula, it also has a torus, which is roughly the same size of the disk. And that torus is rotating. So you said it's a quite complex structure that happened. This probably happened, as I said, about 15 years ago. because the star has not recovered back to the previous phase that it was in the V band. Now that was one example with one star, an oxygen-rich star. But let's move a bit to the other two sources are carbon-rich, and the other two sources I'll be talking about have something that is called obscurations. So in the previous one I showed you, it was a single possibly ejection of a planetary nebula. It happened once, and then the brightness of the source dimmed. Here you have, apart from the canonical pulsation period, and in this type of star is about 600 days, you also see a secondary period that lasts about 16 years. So in the graph here, and you see that being repeated not only in the visual bands, but also in the near infrared. So the hypothesis for this was whether you have a visual, so this is called an obscuration, whether this is caused by a visual companion passing in front of the star, or if you have ejection of dust, and in this case, carbon-rich dust, which can be more dense and can hide the star and certain periods, either hiding the companion or some kind of periodic ejections, which are both very bizarre for a single star, let's say. Now for Vihaya in particular, we know that it's also a very complex object. It's also inclined towards us, so we were able to see the system, but not necessarily the star itself. The star, of course, is too small, but the larger scales, you see a high-speed jet. So velocity is about as high as 180 kilometers per second. It's a bipolar jet. It also has an expanding torus, which is quite large, about 8 arc seconds. And when you look in with Hubble, we found that there is an inner disk from scattered light that's about 0.5 arc seconds. And if you look closer, of course, with an interferometer, in this case with a VLTI, you go to scales of about 30, so from 0.5 arc seconds or 500 milliarc seconds to less than 30 milliarc seconds. So you're very as close as possible to the central star or stars. And now in the mid-infrared, we see that it's not only a star that you need to model the data, but you also need a dust component, possibly a disk-like structure. And we have some previous earlier data with a single telescope, and you can't really, with a VLT, so an 80-meter telescope, you can't really resolve the target at all. So there's been a monitoring of this particular star for the last 16 years, and I'll only show you a few pictures here. The two on the left are from the same wavelength and the same instrument. So it's an L band. The one on the far left is with aperture masking, and the one in the middle is with just simple imaging with NACO. And the one in the middle, you see that basically the envelope looks spherical, with maybe an oblong direction east-west, so along the middle of the image. But when you use interferometry, you can go even further inside, and you find that you are able to detect a disk-like structure, which is elongated north-south. And that's also repeated in the M band. So it's a pattern. The disk is present in the near infrared. You're not able to resolve the central star, but you can easily see the disk. And most importantly, in the last 16 years or so ago, we see that the shape of the disk is changing, or whatever is the material around the central star is changing. Perhaps it's not exactly the disk, perhaps just an elongation of the ejecta in those particular wavelengths. So tentatively from this data, we could measure if there is a companion, a separation and a position angle for the companion, but we have large uncertainties, and we'll be looking into getting, we have some data with Matisse, we look to analyze in the future and to see if this stands. And let me go to the last object for today. As I said, is another carbon-rich star with the obscurations, or what we think is obscurations, because unlike Vihaya, which is bright in the visual as well and easy to observe, even for amateur astronomers, this star is very faint. It's about 20 magnitudes in the visual, so very, very difficult to observe and take proper photometric, to do proper photometric monitoring. And some earlier work in the 1980s up to 2003 or so, it was monitoring in the infrared because it's very bright in the infrared. And you see that around up to about 1995, it was pulsating with a regular pulsation, but after 1995, its magnitude increased by about 2 to 3 magnitudes. So it's much brighter. And the earlier work said perhaps, so this is a work by Fist et al. in 2003, that this long-term variations is either a dust cloud or clouds ejected in your line of sight. And that's why it's becoming brighter in the infrared in J and H, but not so much or not at all in L and M bands. Or you have a quasi-spherical dust shell, so not spherical at all. And either it's moving away of the star, or perhaps, and we were thinking like maybe what if you have a binary companion that creates this kind of secondary oscillation and obscuration. So we went and looked into this star with a single telescope with a Vizier. So this is just imaging in the mid infrared, and you see that at 8 and 11 micron, it's not exactly spherical. So the envelope, the ejecta is not a perfect sphere. It looks more oblong at 8 micron, and there is a strange pattern at 11 micron with Vizier. So we thought it was a good target for Matisse. I will talk a little bit about this later. We're expecting some new observations with Matisse, the new mid-infrared instrument for the VLTI. But we also observed this in the near infrared with aperture masking. So single telescope interferometry. And what we find is a quite peculiar shape for the ejecta. So in the L and M bands, you see the two rightmost pictures, you see some kind of elongation on the towards the north. What in the K band, there is an extra clump or some material that is directed to the west of the system. So that's quite strange. And now if you take the K band image, because you are the shorter wavelength, so your angular resolution is better than in L and M with this instrument. And we try to study a bit what would happen if you had a radial expansion of this material. And what I show in the image is the points A, B, and C. If you had a radially expanding material, it doesn't really match. It's not in the same time frames. So we try to also explore what if you, it's not an ejection of dust clumps, as suggested before. What if you had a binary system? And from the data, we could tentatively say that, okay, if you have a binary system and you assume a circular orbit, you'll be looking at about a period of 180 years. Or if you assume that the secondary period, this obscuration or suggested obscuration event is your actual orbital period, you'll be looking at a separation which is about less than 30 milliarc seconds. So you wouldn't be able to resolve this with this instrument. And that's why we tried to explore this with some new data with the VLTI. But before going into that, so there is an assumption that either you have a binary or, and it's unseen, but what you do see here, so the clump in point C could be the first coil of a spiral arm, because spirals are more common in AGB stars. So maybe you're looking at this the dust component of a spiral. It's possible, but we think it's more possible because we also had analyzed some sub-millimeter data with ALMA. And these, what we see here is a complex spiral system. What I show you here is just three images, one in HC3N, when you see some kind of oblate multi-shell structure. And in SIO, I specifically try to increase the contrast for the central core, but you can see the spiral arm coming up on the top of the image. And if you look very carefully in the CO image, which is the one, the gray one on the right, there are some certain structures extending from the star. And we found that we have about, from these we measured about 12 windings around, if it is a spiral, and the separation is about 1.7 arc seconds. So this will give us orbital period for the binary of about 128 years. And that's much longer than what we kind of predicted from interferometric observations in the near infrared. So tentatively, if you get this kind of period, and again, you assume a circular orbit because we don't really know the inclination of the system. We don't know what kind of, we haven't been able to detect any binary, basically. We kind of know that the mass of the star is about 2.5 solar masses. So you can infer that the mass of a companion will be about less than 1 solar mass. And why we think it's a spiral? Well, since this paper came out and there's more and more papers with ALMA data, there's a lot of work done now in simulations, simulating spirals for different kind of systems. So if you have different eccentricities or different inclinations for the system, and that one looks very close to a spiral, a binary system, so a spiral, but of an eccentric binary and possibly an inclined binary in our line of sight. So let me finish now with a quick summary of everything. So what I showed you so far is that you have a diverse range of equatorial structures of planetary nebula. I hope I convinced you that you can see dense and dusty toruses or flared disks. You can see gaseous rings or gaseous tori, and of course, a lot of bipolar or multipolar or other irregular shapes for the nebula themselves. And but you don't only see those in planetary nebulae, but you also see them in the earlier phase in AGP stars. And now these could be dusty disks that are quite flat looking like, but in most cases for AGP stars, you see spirals. Now, this might be biased in the sense that ALMA is the dominant tool in detection of spirals in AGP stars, and that is mostly now in CO gas, so it will be gaseous spirals. And not so many examples of dusty spirals, but there are a few from AGP stars. And well, what we also see is that the disks in PNE appear to be passive, so they're not exactly, they don't seem to be expand. In any gas material will be outside the disk, or that's what it looks like. But for AGP structures, you see some kind of evolution. So if you have a spiral is still moving, of course, so the material is moving along the orbital plane, and it's still being shaped, as we saw with L2 Puppis. And as I mentioned before, this kind of data can only be obtained with interferometry. So because you need to look into very small spatial scales, less than 1 arc second for sure, to try and find both the disks and perhaps the components. If there's a binary, you might be able one day to detect the system. And it has been shown it is possible with the VLTI and ALMA. But there's more instruments are coming along now. So even ground-based telescopes can actually, you can obtain excellent data with them, because basically you will have more baselines than you will do with a single telescope, even perhaps even with a JWST, and perhaps because these stars are very bright anyway. So you might have other points to consider when you want to continue research on this. And now, a few questions you might want to take home is what we see more in AGBs is spirals or rotating disks compared to more stable disks, unlike planetary nebulae. But is this the normal? We don't really know because we don't have a big enough sample to study this. And there's also the case of some symmetric AGB, so stars that look like it's a single star, not a binary, and its ejecta looks like a perfect sphere. So that's also possible, and it's something to consider. It doesn't mean that they're all binaries anyway. One of the ways perhaps to find binaries is to look for obscuration events, but that would mean to look into a lot of, if possible, the ones that can, of course, be detected by long-term monitoring in the visual or in the near infrared. That, of course, takes a lot of time. So you can still go through archival data like AIVSO. There's at least 6 known so far that have bona fide obscurations. Apart from Vihaya, there's 5 more. And well, if you have this kind of time and research, are able to do this research, perhaps you can start building, telling more about the statistical analysis of a large sample of AGB stars. And there's also other things to consider, of course, because perhaps it's the kind of binary you have that is the drive for the kind of disk or structure that you will get. Because if you have a short period binary, you will get more strange structures like jets or ANSI, or very small disks. But if you have a long binary, that's when you get spirals. The longer, so depending on the orbital separation, of course, you will get different kinds of shapes being formed in the ejecta. And in the future, we were expecting some data on II loop with imaging interferometer, the imaging instrument of the VLTI, but COVID, so we didn't get anything. We got some data on Vihaya, and we are analyzing those soon to see if there's something there, again with Matisse. We also have some new data on ILUP from simple imaging, and we wanted to do a comparison between imaging, simple imaging, near infrared and mid infrared interferometry. So we'll see how that goes. And there's of course another paper coming out, well, hopefully soon, on another star which has an obscuration like Vihaya, and it's R4, and there's some very interesting results from the VLTI. So I'll leave you with that, and I'd like to thank you for your time.
Thank you very much, Foteini, for this interesting talk. Are there any questions? Either raise your hand or just speak directly. If there is no question right now, or people are warming up, I have a couple of questions. One is a bit technical, and it has to do, you mentioned at some point in your talk about doing single telescope interferometry, right, with a mask. Can you sort of like elaborate a bit on that? Because if you do single telescope and you put a mask, clearly the largest baseline that you get is similar to the size of your mirror, right? So you don't gain in angular resolution. What does the sparsity of the image that you get provides to you?
Well, you do get a bit of better resolution. As I showed you earlier, perhaps.
But why? Because you don't saturate, because you get less light?
You don't saturate, and how to explain? you're not as affected by atmospheric transmission as you are with the stable imaging. Because in this case, you're using what we use to make the images is closure phases, and those are not affected by atmospheric transmission.
Okay. Okay. Yeah, I need to think a bit about it. And okay, and then on another topic, you mentioned earlier on that it seems that like something like 80%, if I don't recall, it was one of your introductory slides, 80% of the PNEs that you see show some sort of asymmetry, non-sphericity, right? And is this from, I don't remember well, right? But in textbooks, we typically say that maybe half or 60% of the stars are binary, right? So do you think that all these asymmetries are associated with binarity, or could it be that there are other reasons why you may see this asymmetric or sort of like elongated shapes on PNEs? Can we get it from a single star, for example, a fast rotating star that would have a disk?
I don't think so, because those stars are not rotating fast enough. It's not like, let's say, massive stars.
I see.
And but to form a disk, you wouldn't be able to do this without the binary, because then you would have the ejector going to, well, expanding more or less spherically. So how do you constrain if it's not rotating? Because it's not, the rotation is very low, and the star is quite big actually. So how would you form it otherwise? And I say 80%, so that kind of also includes elliptical planetary nebulae, and not only the bipolars, but there's also the case of how you're looking through the nebula. So you could be looking at from the top inside a bipolar nebula, and it looks like a sphere, but when you get the kinematics, then you know that it's actually not spherical at all.
Okay. Okay. Thank you. There is a question by Marcos Polkas. He says that I can read it for you if you want to, or for the audience. He says, nice talk. Do models and chemo and magnetohydrodynamical codes motivate the profiles used to fit the dusty Tori? Are obscuration events able to be modeled with numerical codes?
I'm not familiar with any MHD models for these. The simulation so far, I think, is just hydrodynamical. So, no, hang on. There is a few, no, correct. There is a few MHD models from PN specifically where they try to model the jets and how you get the launching of the jets. And, but I'm not, sorry, I don't remember now if they actually include a disk in their analysis in the model.
Okay. Someone else?
I think I missed the second part of the question. It was obscuration events.
Yeah.
Are obscuration events able to be modeled with numerical codes? As in, can you reproduce the pulsation, or I'm not sure what you mean here. If you have a binary companion, you wouldn't have just the canonical the pulsation period of the AGB star, but there will be another. If it passes in front, of course, of the AGB star, you would see the secondary pulsation from the companion. I don't know if that helps. Sorry.
Okay. Someone else?
Can I say hello to Foteini? I haven't seen her for a long time.
How are you?
Good to see you. Thank you for your nice talk and interesting work. It's amazing what can be done with interferometry, and I agree with you. It's this way that we will get answers to these long-standing questions. So I'm glad to see you, and I'm happy for your progress.
Thank you, and glad to see you even if it's online. What can we do?
Yeah, just as a side note, while you were talking, I got a phone call from Despina on a separate Hadzidimitriou. And she said, hopefully I'm not interrupting. And he said, well, a bit you are, and you know who is talking. So she was very excited to hear that you were giving a talk. So she sends her greetings as well.
I'll write her an email.
Send her an email. Yeah, she would be
Thanks
glad to hear from you. So I don't see any hands being raised. So I would like, on behalf of all of us, to thank Foteini once more. And hopefully the situation will improve on another front, and we'll be able to have her at least visit the first island where she started her studies in the near future, and have the opportunity to have her from nearby to talk to us. Thank you very much, Foteini.
And I'll be glad to come back at some point. Thank you for having me. Bye-bye.
Okay, bye everybody.